This video will show some of the basic geophysics tools in Geoscience ANALYST Pro, covering the following themes.
So the idea here is that we have some information. So we have our DEM and a Datamine model surface. So here I'm just going to drag and drop it in. We have our gravity data as a point set. And we have a model.csv.txt, so an ASCII-based block model. And that's what we're going to start with. And so that model has a rock code that has been prepared by someone, most likely a geologist, and it has been imported and exported through some type of geologic modeling software.
I'm just starting with a blank Geoscience Analyst project here, and I'm going to load some data. So I've got a topography surface in Datamine format, and so I've got my Windows Explorer here. I'm just going to drag and drop that triangulated surface into the Geoscience Analyst viewer. There we go. So we've got the topography surface there. It looks yellow. If you want to make the yellow stuff disappear, just click on this triangles tab, and you don't see the mesh of the object. We can color it by elevation. In the data colors window here, we can just make that color stretch linear and maybe choose a more suitable color bar for a DEM. So there's our DEM surface. So we now load some resistivity data. So this is just in UBC observed data file format. Just again drag and drop that into the viewer window, and you can see here that we're seeing the pseudo section of the resistivity data. So these are normalized voltages or resistances.
I'm going to start by just the data. And here I have a grid of data that looks like this.
So in the assets, I have two files, a VTEM survey and a DIGHEM survey, and they're a GDB format, which is pretty standard. So I'm just going to slide those surveys in. So that's pretty simple. And I'm going to do the VTEM as well. Okay, so all it's doing here is assigning the XYZ coordinates and then the data. There we go. So now we have data in the camera.
So the first thing I'll do is I'll import that VP model into Geoscience Analyst through that simple drag and drop. And here we have it. So you'll note that these cells are actually vertical prisms that conform to the geological boundaries. And in the data colors panel down here, you'll see what each of these colors corresponds to. Now, I've already set the color settings in another workspace, so I'll just load them into this one. Like that. And maybe I'll change the color of my basement. There you go. So here's some magnetic survey that they've done. These are the observation points. They have some magnetics data. So the goal is that we're going to create a 2D grid around these, and then we're going to interpolate the data from the points onto the 2D grid. So we'll go to the Utilities menu, 2D Grid Designer. Again, you can select the object from the drop-down menus. I'll use the arrow, pick it out, and you can click on that light bulb which says suggest dimensions. Yes, please. I don't want to come up with them myself. Awesome. So it drew a 2D grid around my data. So you can always play around with the origin. In this case, it seems to be pretty good. And the origin is this guy right here. So that's these coordinates. The grid size is also seems quite suitable. Feel free to change that as well if you like. And the cell size we will change. It seems like these 30 by 30 meter cell sizes are really small for our data. So we'll change this to 100 by 100. And then it tells you the number of cells in the U direction and in the V direction as well. So that's 33 this way and 51 that way, with a total of 1,683 cells. You can put in an azimuth and dip when you're creating a 2D grid. In this case, it's not really necessary, but that is an option if you'd like. And we'll name this 2D grid. And click create. Great, so a key point right now is to close this dialog box once you're happy with it. Right now we're looking at the preview plus the grid that was created. So if you shut that down, now it should be fine. I find it easier to see the data if it's something other than blue, maybe a gray, so that the data stands out a little bit more, like that. And maybe make it a little transparent as well. Okay. Let's show the grid. Okay, so we've created our 2D grid. It's right here in our objects tree, but it does not have any data attributed to its cells yet. It's just an IJ and an XYZ for the centroids, and that's kind of dull. So we're going to give it that magnetics data. So to do that, we'll go to Utilities, Minimum Curvature Gridding. Let's pick that 2D grid. Let's pick the source object. That's the one that has the data right now, and that's the mag observation points. The property that we're going to be interpolating is magnetics. We'll leave these as default and change only max extrapolation distance to 150. So if the data point, if the center of the cell is more than 150 meters away from our mag observation point, from the nearest one, it'll be given a no data value. We'll leave all the other settings as default. There's a bunch more info on them in the help, but for now we can just leave them as is and click OK. Great, so let's take away those mag observation points for now and look at that 2D grid. I'll get rid of that transparency now. I'll stop showing the grid. And one thing that you can do here is make it smooth. This video will show you how to remove regional transfer potential fields data using the basic geophysical tools in Geoscience ANALYST Pro. This is a key step to ensuring the quality of the input data for your unconstrained inversion. We will remove the trend from gravity observation data. You can access this utility from the geophysics menu or by right-clicking on the object. Select your object, whether it be points or a 2D grid, your magnetics or gravity property, and choose the order of the 2D polynomial trend, first, second, or third. This will compute a best fit trend and remove it from the data. The equation for the trend is returned to the console panel. As you can see, once the trend is removed, local anomalies that were previously hidden or hard to interpret are now accentuated. This video will show you how to apply Fourier filters on 2D grids using the basic geophysics tools in Geoscience ANALYST Pro. We will start by applying a reduction to pole filter on our magnetics data. You can access this utility from the geophysics menu or by right-clicking on a 2D grid. Select which filter you want to apply, in this case, RTP Fourier filter. Select your 2D grid, its magnetic property, and specify the inclination and declination of your area. A new property is created with the name of the applied filter as a suffix. You can also apply more filters on the RTP filter data. For example, a first vertical derivative filter.
Select the filter first vertical derivative for your filter, your 2D grid, and RTP filtered magnetics data.
Okay, so let's say I have this data on here now. I have my RTP filtered and my trend removed data, etc. And I want to run an inversion. But for that, I need to put this data on my observation points. So we can do a transfer from a 2D grid to observation points. So that'll be in Utilities, Transfer Grid Data. From the 2D grid, here we can unselect that, and we want to transfer that first one on the list, the magnetics first order trend removed. And we're gonna transfer it to our mag observation points right there. And we'll click OK. So we'll turn on those mag observation points, and you have your magnetics, and you have your magnetics first order trend removed. So you can go between these two and compare them.
So the next thing we want to do prior to inversion is to create a block model or a mesh for the inversion. So if I turn the topography surface off and zoom in, so here are our lines, and I can go to Utilities, Block Model Designer, and I'll just move this out of the way a bit. And the object that we want to use here is the DC resistivity object. Click on this button here, and you can just draw the extents of your mesh. So there it is. And then we can set up some parameters. I want to move the top of it to 350 meters. The maximum depth extent I'll make 2.5 kilometers. And then the X, Y, and Z cell sizes, I'll just make 35, 50, 35. And you can change the proportion of the mesh that is the core. So I'll just set that to 25. And you can see that the number of cells in the mesh is updating dynamically down here as we make changes. So I've set that to 25. Because this is a UVC inversion, we have to add some padding. So I'll tick on the padding box there, and then I'll add a couple of kilometers of padding in the east, west, and north, south directions. So there we are. And we can make those padding cells expand with distance away from the core. If you hover your mouse over this button, you get to see what the expansion factor is set at, currently 1.2. I'll set it up to 1.4. So I'll just, that's 1.35, a bit more. There it is, 1.4. So, and this mesh that we're going to create is going to be called block model. So click the create button and move this out of the way. We've got a mesh. So if I zoom out, there's our mesh in 3D with the data in the core.
This video will show you how to compute unconstrained inversions using the basic geophysical tools in Geoscience ANALYST Pro. We will compute an unconstrained inversion on regional magnetic data. You can access this utility from the Geophysics menu. Using our unique VP geophysical technology, this utility can invert 3 different kinds of data: gravity, total field magnetic data, and gravity gradiometry. Select your observation points, the magnetics or gravity data, and set an uncertainty level. For magnetics data, you must also specify the field strength, inclination, and declination of your area of interest. Finally, select your topography and block model. Once all the inversion parameters are specified, click OK. The inversion will compute weighting functions, compute derivatives, and then perform forward modeling and inversion iterations. Once the command is run, the error data misfit is returned to the console panel. The computed response of the final model is stored on the data points. To further assess the results, analyze the difference between the observed and predicted data, called the residual. The inversion recovered model is also found in the mesh object. Now the anomaly can be visualized and analyzed in 3D. For example, we can create ISO values from the anomalous susceptibility.
To create the survey, you go to Panels and then Survey Designer. And it's right here for me because that's how I had it before. If you do have it taken up way too much real estate here, you can always kind of like put it on top of another panel so that then they're tabbed and you can flip between one and the other. We're going to be doing some airborne gravity surveys. And this will be a new survey. You have a choice of choosing an existing curve, but in this case, we're going to be creating a brand new one. And this will be a fixed wing. And for the origin in the azimuth and the length, we'll be drawing it on the survey. We'll be drawing our survey. So here it's another one of the examples where I like to put it on parallel view. You don't necessarily have to, it's just fine to do it in perspective view as well. So you can click on that left click, drag to draw survey line icon. And I'll just draw a line down like this. My line is just about crooked. So I can go back to perspective now. And I'll fix that azimuth so that it's 180. And the length of it looks pretty good to me. One thing you can do here is bring that Z origin up. Right now it's where my section was, so at -300. You can change that up to 320. And that's approximately where the topography is on that model. Okay, so I've got myself one curve, but I need a few more. So let's put in, let's say 21, and you might have to play around with this number. In this case, I figured that 21 works for me. And let's change the line spacing to 150, like that. Let's also change the station spacing. In this case, each node in that curve, so each station in that survey is 15 meters apart. Let's change that to, let's say, 25. And you can experiment with all the different alignments as well. So here it's saying that that one that I had drawn, that one with the origin, is on the left-hand side. And we'll put a terrain clearance of 30 meters. We'll also choose our topography. So what that's going to do is that it's going to be draping these curves on the topography plus 30 meters. It still looks pretty flat. That's, again, we're in Manitoba, but if you're looking closely, there is some topography to those curves, and you can always change the vertical exaggeration to see that more clearly. So the next thing that I'm going to be showing is a pro feature, and that will be how to validate your geological model with your geophysical data. So for that, we need a geological model, which is what I'm showing right now. It's got all of these classes, including our ore body in red right here. Then I also need some geophysics data. I've got a fixed wing falcon that has airborne magnetics data. Maybe here you go. So I'm going to be adding a column to my geology model, and I'm going to call it mag contrast.
I'm going to give that ore body a mag contrast of 0.05, and I'm going to leave the mag contrast for all the other units or lithologies as 0. And you'll see that created new data in my block model, where, well, there you go, where that that ore body has that value of 0.05 and the rest is all 0. All right, now I'm ready to compute my forward model. So I'll go to the geophysics menu, compute forward model. This is a magnetics type. I'll choose my observation points. I'll set a field strength, an inclination, and a declination. I'll choose my topography surface, then that block model with that data that we just created, that mag contrast data. And now that I've selected everything, I'll click OK. So now we have a new data here. It's called forward model. You can flip between the two of them to compare these two different data visually. But there's another way to compare them, and that would be to use the 2D profile viewer. So to do that, you can go to the panels menu, 2D profile viewer. And I'll open this up. There. I'll select this curve, and it right away drew a profile of my airborne mag data. I'll add data, I'll add that forward model, and I'll just change the color really quickly. Maybe a blue would be good here. And change this to this. And I'll add a legend. So now we can see if the response from our geological model, which is this blue profile, matches the observed geophysical data, which is this purple-pink profile. And right now we're looking at the profile along this specific line, the one with the anomaly on it. And I can flip through the different lines by either playing with the slider or increasing or decreasing the number here.